Welcome back. We are doing some problem sessions, and last class I ended with this problem where I left it in the middle of the problem, and I will complete it now. So this is actually easy to finish this problem now. So if you recall, in this problem we are asked to, so let's see, 6. In each of the following extensions, first show that it's Galois, and then show that then find the Galois group and find all the intermediate fields. Okay, we are looking at various fields in this problem, and the last part we are looking at the splitting field of this particular polynomial over various finite fields. We did F2, then it is just the F2 itself is the splitting field because the polynomial splits completely. The same happens for F3. F5, there is one root, and after you factor it out you have a quadratic polynomial. So the splitting field will be a degree 2 extension, and the Galois group is a Z mod 2Z. And finally we are doing F7, and what I wanted you to check, which is written in red here, is that this polynomial is irreducible. Simply check that it has no roots. Because it's a degree 3 polynomial, it suffices to check that it has no roots, and you can conclude that it's irreducible, and that's a trivial verification. So then we took the splitting field, and let's say alpha is a single root and we adjoin F alpha. So then in general, when you add roots of a cubic polynomial, irreducible cubic polynomial over a field, you can always add one root to get a degree 3 extension. Now the question is, are other roots already in F alpha or other roots need to be added extra? So these two possibilities are listed here. Either the other roots are already in F alpha, in which case the K itself is equal to F alpha, the splitting field is F alpha, and the degree of the splitting field is 3, and hence Galois group has to be Z mod 3Z because it's a degree 3 extension, and whose Galois group is going to be of order 3. The second possibility is that the roots are not in F alpha, in which case you will have to add them, and then it must be degree 2 exactly, because after you factor out x minus alpha from the polynomial in question, this is degree 3, this is degree 1, so this will be degree 2, and by the assumption that F alpha has no roots, no other roots, this G will be reducible over F alpha, and that would be the degree. In this case, the degree of K over F alpha will be 2. Okay, so this is just a parenthetical remark. So in our problem, which of these cases happens? So I claim that K is in fact F alpha, and for this it's a simple statement. We note simply that once alpha cubed is 2, what is 2 alpha cubed? So alpha is in K, alpha is in F alpha, alpha is the root of x cubed minus 2, so alpha cubed is 2. So what is 2 alpha cubed? So this is 2 cubed alpha cubed, so that means it's 8 alpha cubed, but 8 is 1 in F7, right? So this is alpha cubed, which of course is 2. So that means 2 alpha is a root. Similarly, if you do 4 alpha cubed, you get 64 alpha cubed. So this is again 63 is a multiple of 7, so this is alpha cubed, so this is right 2. So 4 alpha is a root. So once you have a root, the other two roots are simply 2 alpha, and so the roots of x cubed minus 2 in K, in F alpha in fact, are alpha, 2 alpha, 4 alpha, and hence K is F alpha, as I claimed at the end of last class. So the point is, there is a cube root of 2 or cube root of 1 in F7, namely 2 and 4. So once you have a cube root of 2 and a cube root of 1, you can multiply them to get another cube root of 2. Okay, so this implies that Galois group has to be a group of order 3, and there is only one such group up to isomorphism, and there are no non-trivial intermediate fields, right? Because it's a degree 3 extension. So if you take any field here, the product of this number and this number is 3. So one of them has to be 1, in which case that L will be equal to F or K alpha. So in general, if you have a prime degree extension, it won't have any proper or non-trivial intermediate fields. So that solves this problem. Okay, so this completes this particular problem. So let's do a few more problems. So the 7th problem I want to do is the following. Let K over F be a Galois extension such that the Galois group is isomorphic to Z mod 2Z cross Z mod 12Z. Okay, so this is a problem which gives you an idea of how to apply group theory to derive information about the fields that we are working with. So the problem asks you to find the intermediate fields L such that they have 3 properties. L colon F is 4, then L colon F is 9, and finally the Galois group of K over L is isomorphic to Z mod 4Z. Okay, there are 3 parts to this problem. So given a Galois extension whose Galois group is Z mod 2Z cross Z mod 12Z, actually the question is find the number of intermediate fields So I can't really find, L, because K over F is an arbitrary extension. We have no information about it other than its Galois group. So really I can only do the number of intermediate fields with these properties. So let's first do A. So let's draw the picture that we are now comfortable with. So given extension is K over F. What is K colon F? K colon F, because the extension is Galois, this is the order of the group, which is 24, because it's a group isomorphic to Z mod 2 cross Z mod 12. So that first is a group of 2, order 2, second is a group of order 12. So the product will have order 24. And we want this to be 4, that means this to be 6. So implies K colon L is 6 and if L colon F is 4. Okay, so now what are intermediate fields L with this property? By the main theorem, any intermediate field such that K colon L is 6 must be the fixed field of a subgroup H of Galois group such that order of H is 6. So now if you remember the main theorem gives a bijection between subgroups of the Galois group and the intermediate fields, and the order of the Galois group is the top degree, and the index of the order of the subgroup is the top degree, index of the subgroup is the bottom degree. So this is equal to 6. So the number we are looking for, so the number of intermediate fields L such that K colon L, or this is the given problem, L colon F equals 4, this is equal to the number of intermediate fields L such that K colon L is, because L colon F is 4 is exactly the same as saying K colon L is 6, and this, more interestingly, is the number of subgroups H of the Galois group such that order is 6. Okay, so now we have reduced the whole problem to find the number of order 6 subgroups of Z mod 2Z cross Z mod 12Z. Remember, Galois group is isomorphic to Z mod 2 cross Z mod 12. So the number of subgroups of order 6 of the Galois group is exactly the number of subgroups of order 6 of this very nice group, concrete group. Okay, so if two groups are isomorphic, the things like number of elements of a fixed order, number of subgroups of a fixed order, and order of the group itself, they are all same for both groups, right? So now we have reduced the whole problem to a purely group theoretic problem. This is a group theoretic problem. Okay, so what was originally a field theory question became really a group theory question because of the main theorem. That is the crucial ingredient in this solution. Okay, now I will just quickly tell you how to do this. You all know what Z mod 2Z cross Z mod 12Z is. So first note that if order of H is 6, in general H can be either this or the cyclic group of order 6. But H is a subgroup of Z mod 2 cross Z mod 12. But this is abelian. So H is abelian, so basically this cannot happen. So we are looking for cyclic groups of order 6, right? So H must be cyclic. So we will know the number of such H. We can find the required number if we find the number of order 6 elements of Z mod 2Z cross Z mod 6Z, 12Z. Okay, so that's this is what we need to find now. Note that the number of groups of order 6 is not equal to the number of order 6 element, because if you take an order 6 element, its inverse will also have order 6. So these two will give the same group. So it's really the number of order 6 elements divided by 2. But now we are in business because we have to find the order 6 elements. So now I'm going to use additive notation, right? So 0, 1. I mean, I will omit writing bars here because it's cumbersome to do that, but you all understand that 1 plus 1, for example, is 0 here, and I will, by abuse of notation, call this. Okay, for example, now let's try to write down what are the order 6 elements. So what are order 6 elements? Order 6 elements are, I can take 0 in the first coordinate, then the second coordinate must have, so order 6. So this is a fact that I'm going to use, it's a useful fact. If you have an abelian group, okay, so G1 cross G2, let's say G is this, G1 and G2 are abelian. Order of A comma B, where A and B are in G1 and G2 respectively, is LCM of orders of A and order of B. Okay, the order of that tuple AB, so that's in G, is LCM. So in order to get order 6 element, one possibility is, so we want order 6, so this could be LCM of 1 and 6, right? So 0 is an order 1 element in Z mod 2Z. So to get an order 6 element, I have to take 2, for example. Okay, so this is an order 6 element, and its inverse of course will be 0, 10, because the inverse of 2 is 10. So one group, so first group of order 6 is simply 0, 0, 0, 2, 0, 4, 0, 6, 0, 8 and 0, 10. So this is 1, 2, 3, 4, 5, 6 elements. Okay. Now this is the only group which first coordinate is 0. Now what are the other elements? So these are some possibilities. On the other hand, we can also do order 6 equals LCM of, let's say, now you put 1 in the first coordinate, so that is 2. So you can put 6 here, or you can also do LCM of 2 and 3. So this now gives you more possibilities. So that means you take 1 and order 6 element. So I'm going fast about this because this is just, standard group theory, but please carefully watch this if it's not clear to you. And to get, so this is an element of Z mod 12, Z mod 2 cross Z mod 12, and it has order 6 because you can write down, for example, all its multiples. The 6th multiple will be 0, 0, and the other element will be order 3 element will be 4. Okay, so these are two order 6 elements in Z mod 2 cross Z mod 12. So in fact, this will give its inverse. So 1, 2 and its inverse will be 1, 10, and its inverse will be 1, 8. Okay, so 4, 8, 12. So 4 is an order 3 element. Okay, so these are the second group of order 6. Okay, so I'm just explicitly writing this. 0, 0 of course will be there, but the generator is 1, 2, and then it's twice that is 2, 4. Add 1, 2 to this, you get, so 2, 4 is actually 0, 4. You add 1, 2 to this, you get 1, 6, right? And you get, then add 1, 2 to this, you get 0, 8. Add 1, 2 to this, you get 1, 10, which is the inverse, and you stop. So 1, 2, 3, 4, 5, 6. Third group of order 6 will be generated by 1, 4. So 1, 4, its twice will be 0, 8. 0, 8 plus 1, 4 will be 1, 8 plus 4 is 0. Then you add 1, 4 to this, you get 0, 4, and then you add 1, 4 to this, you get 1, 8, which is the inverse. So 1, 2, 3, 4, 5, 6, 7, 6. So these are the 3 groups, and you can check that these are all the subgroups of order 3, order 6. Okay, there can't be any more subgroups of order 6. So this is easy to check because there are only 6 elements of order 6 constructed this way. So this is these are 2 of them, these are 2 more, and these are 2 more. Okay, so the answer to the part A is 3. There are 3 fields L such that L colon F is 4. Okay, so I hope this is clear. I had to go fast with this, but this is just the main thing I want you to be comfortable with is the reduction of the problem to group theory, and then treat the group theory problem as a separate isolated problem and just work out. This is a very concrete group to work with, and it's 24 elements. You can write down and check that these are all the order 6 subgroups. Now let's go to B. So we have to find subfields, intermediate fields such that this degree is 9. But this is actually a very simple, trivial question because this is 24. So this cannot be 9. So the answer in B is 0. Right? What is the number of subfields, intermediate fields L such that L colon F is 9? It is 0 because there can't be. So this is not possible. Okay, and so there are no intermediate fields with this property. And finally, let's look at L such that Galois group of K over L is isomorphic to Z mod 4Z. So this is more direct. So the number of L such that Galois group, okay, so let's say number of L such that this happens is equal to number of subgroups of Z mod 2 cross Z mod 12 which are isomorphic to Z mod 4Z, right? Because if you have K and L and F, this has to be the number of any intermediate field with this property has to be the fixed field of a subgroup H which is isomorphic to 4Z, and there is a bijective correspondence between all such L and all such subgroups. So how do you find the number of subgroups like this? exactly as we did in 6, part A. So we found number of subgroups isomorphic to Z mod 6Z, and here we have to find number of subgroups which are isomorphic to Z mod 4Z. So I'll give you the answer. Answer is 2, and I will let you check the solution. So show this. Okay, so because we have done part A in detail, so I won't give you the details here, but find order 4 elements. Okay, so you can take 0, order 4, so 1 and 4 will give LCM 4, just like before. So 0 has order 1, but what is a degree 4 element? Order 4 element, you take 3. So and then you take its subgroup generated by this. So I am really giving you this, and you have to verify that these are the only things. And the other possibility is you can take 1 which has order 2, and to get order 4, the other thing has to be order 4. Okay, so again you have to have order 3. So these are only, check that, these are the only subgroups of Z mod 12 2 cross Z mod 12 which are isomorphic to Z mod 4. Okay, so the answer is 2. So the part C has answer 2. So the number of intermediate fields which with Galois group K over L is isomorphic to Z mod 4Z is exactly 2. Okay, so let me now continue to the next problem. I want to do 2 more problems. So all these problems are hopefully giving you a more comfortable picture of what we have done so far, and they illustrate the theory that we are trying to develop. To study field theory, we are reducing it to some questions on group theory. Okay, and then you will see much more substantial applications later, but these are all nice problems to know how to solve because they help you understand the theory well. Okay, so the next problem that I want to do is a problem that I remarked on earlier. So this is the problem which asks you to show that give an example of a field extension of a finite extension of fields, let us say K over F, such that there are infinitely many intermediate fields. Okay, so you want K over F finite, but this will have infinitely many intermediate fields. Okay, so I gave immediately after proving the main theorem, we showed that if you have a separable finite extension, there are only finitely many intermediate fields. So we know that any example that we can have this property has to be inseparable. So immediately we have to go to characteristic prime. Not only that, we have to go to infinite fields of characteristic prime because finite fields are perfect. So any extension is separable. So I'll give you the example that works, and I'll explain to you what we how we prove this statement. Okay, so we take f to be f2 bracket t comma u. Okay, so these are variables. So far we have looked at rational function field in one variable to construct some examples of normal non-Galois extensions. Here we are taking rational functions in 2 variables. So let me not belabor this point, but the elements of this are ratios of polynomials in 2 variables. So this is nothing but quotient field of f2 square bracket tu. So you take polynomial ring in 2 variables and take its quotient field. That means elements of f, capital F, are simply going to be ratios of polynomials f by g, where f and g are polynomials in 2 variables. Okay, and in this what we do is consider x square minus t and x square minus u. Remember, in the earlier example of a normal non-Galois extension, we took one variable and this particular polynomials. We take now 2. So we are taking 2 polynomials over capital F. T and U, remember, are constants because they are in capital F. Okay, what do we do is we let alpha, beta be roots of, let's call this F, respectively in a splitting field, let's say of Fg. So I can always construct a big field where they both split. So now within that, so alpha is the root of x square minus t, beta is the root of x square minus u. So alpha square is t, beta square is u. So now let k be f alpha beta. Okay, so this is inside that splitting field. This is in fact the splitting field, as if you think about this for a bit, but I don't care. K is this. So now my claim is K over F does the job for us. K over F is the finite extension which has infinitely many intermediate fields. So let us prove this. This is a finite extension and it will have infinitely many intermediate fields. Okay, let's prove first that, first claim that it is a finite extension. In fact, it is a degree 4 extension. Okay, so this is very easy, let me just quickly do this, but in the process I want to maybe explain carefully what is required. So K colon F is 4 is the claim. So obviously we know that K is F alpha beta. The trick is to do F alpha and then F. So if I show that both of them are 2, then I am done. Okay, so we do know that. Okay, so the proof is basically here. I am going to write this here. So we first note that alpha is not in F. Okay, because t is a variable and it has no square root in F, which is Ft Tu. I mean, this is a statement we mentioned before, right? Because you cannot find a ratio of two polynomials whose square is t for degree considerations. Okay, so basically let me write it here. Alpha is a square root, loosely speaking, of t, beta is a square root of u. So they don't exist in capital F. F itself doesn't contain square roots of t or u. So alpha is not in F. So that means F alpha colon F is strictly more than 1. On the other hand, alpha satisfies x square minus t, which is a polynomial in Fx. So that means F alpha colon F is less than or equal to 2, right? Because it satisfies a degree 2 polynomial. So its degree of alpha is at most 2. Maybe it satisfies a linear polynomial also, in which case degree will be 1, but it does not. So hence okay, so this is 2. So the second part is to argue that K colon F alpha. So I'm sorry, I'm sort of writing it all over the place, but I want to keep everything in front of you. So first note that F alpha is a degree 2 extension of F. So now first note that, so I want to prove this, but we do know that since beta square is, which is of course u, is in F, which is in F alpha. So note that K is actually F alpha bracket beta. So we do know that beta generates K over F alpha. It satisfies a degree 2 polynomial, namely x square minus u, which lives in capital F in fact. So it certainly lives in capital F alpha. So let me draw some lines. So this is the original picture. Okay, so this can be at most 2, right, because it does satisfy a degree 2 polynomial over f alpha. So now the question is it 2 or 1? So we now claim beta is not in f alpha. Then these are distinct fields, k and f alpha will be distinct fields, and hence it will be 2. So why is beta not in f alpha? So this is because suppose beta is in f alpha. If beta is in f alpha, then we can write beta, because f alpha is a degree 2 extension, beta can be written as some a plus b alpha, where a and b are in f. Okay. So this is a standard argument, but I will work through this because first time I am doing this, or maybe I have not explicitly done this before. So we have this, right, because f alpha is a vector space over capital F with basis 1 and alpha. So we have this. So now let us square both sides. So beta is this, and of course, I mean, let me first get rid of trivial cases. If a is 0, this implies beta equals b alpha, this implies beta square equals b square alpha square, this implies beta square is u, alpha square is t. So t equals b square u, but this means t and u are dependent variables, but that is not the case. Okay, t and u are independent variables. I should really write this, they are independent. They are independent variables. So there is no polynomial that is 0 if it has non-zero coefficient. So this cannot happen. So a cannot be 0. On the other hand, if b is 0, that means beta equals a, but this is in f. So this is also not possible, because we already agreed that alpha is not in capital F. Similarly, beta is not in capital F, and hence we conclude that AB is non-zero. So we are going to use this later. Now beta equals a plus b alpha. So let's square both sides. So we get beta square equals a plus b alpha whole square, which is a square plus 2ab alpha plus alpha or b square alpha square. This implies u, which is beta square, is equal to a square plus b square t, because alpha square is t, plus 2ab alpha. But that means alpha equals u minus a square minus b square t divided by 2ab, because ab is non-zero, that we have established. This is a valid element of the field F, because u, a, b, t are all in F, right. So since u, t, a, b are in F, so this is not possible. Again, this is a contradiction. Alpha is not in F, so this is not possible. Hence beta is not in F alpha. So k colon F alpha is 2. So I am justified in putting a 2 here. So that means this is also 2. Okay. So hence k colon F is 4. So it is a finite extension. So it is a finite extension. Next step is to show that it has infinitely many intermediate fields. So let's do this. So let, for any a in capital F, let L sub a be defined as f of alpha plus a beta. Okay, f sub alpha plus a beta. So of course there is an intermediate field of the extension. So k is here, which is f alpha beta. La is here, which is f alpha plus a beta, and f is here. So this is a degree 4 extension. So we are going to claim now that these are all distinct fields. So La is different from Lb if a, b are different. Okay, La is equal to not equal to Lb if a and b are different, and hence there will be infinitely many. Okay, so also, yeah, f has infinitely many elements. So we are done since F has infinitely many elements. Note that F2 has finitely many elements, but capital F is F2 round bracket TU. So you can take any polynomials of arbitrary degree. So F is certainly infinite field. Remember, in fact, if you take a finite field, you cannot hope to get an example with this property, meaning having infinitely many intermediate fields, because finite fields are perfect. So F has to be infinite, but that it is, because you can take arbitrarily high degree polynomials. So you can take A and B to be A and B from infinitely many elements, and LA and LB are different if A and B are different. So LA, in fact, LA is never equal to K or F, but you don't care, because maybe for one LA is K, for another A, LA is F, but all the other things are going to be proper intermediate fields. Okay, why is this? So the proof is, so this is a simple calculation, I will show you now. So suppose LA equals LB, then what is the problem that will happen? So then LA, remember, is F of alpha plus A beta. So this is in LA, so this is in LB. Okay, so that means alpha plus A beta is in LB, but then we do know that alpha plus A beta minus alpha plus B beta is in LB, because LB also contains alpha plus B beta. In fact, LB is generated by alpha plus B beta. So the difference between these two is in LB. But what is the difference between these two? You get A times beta minus B times beta. So A minus, so alpha cancels. So A beta minus B beta is in LB. That means A minus B times beta is in LB. But A minus B is, so assume, of course I should say assume A is not equal to B. So A minus B is non-zero, is an element of F, of course, because A and B are elements of F. So A minus B can be cancelled to get beta is in LB. This is the thing that I am after. So you cancel by, you divide by A minus B or multiply by A minus B inverse, you get beta is equal to LB. Now I claim that this is not possible. So if beta is in LB, this means A plus alpha plus A beta, which is in LB of course, minus A beta is in LB, right? Because this is in LB and this is in LB. Alpha plus A beta is in LB by hypothesis, and A beta is in LB, so A times beta is in LB, because A is also in LB. So A is an element of F, so it is certainly in LB. So this difference is in LB, that means alpha is in LB. That means both alpha and beta are in LB. Okay, so in fact what I will now show is that LB, okay, so actually I need to do a little bit more work, but immediately we conclude that LB contains both A and B, and it of course contains F, so it contains K, right? So beta is in LB, alpha is in LB, so F is of course in LB, so F alpha beta is in LB, but F alpha beta is K, and hence K equals LB, right? Because LB is an intermediate field. So this gives, by what we have already showed, this gives this, okay? But because K is a degree 4 extension, and so to finish we claim now, actually yeah, I didn't think we need this, but we need this. If LB colon F is 2, it will not be 4, okay? So basically what I want to claim is this is less than 4, okay? Why is this? Okay, so LB recall is F, this is very easy, A alpha plus B beta, right? But what is alpha plus B beta whole square? this is equal to alpha square plus 2 b alpha b. So actually now recall that we are in a characteristic 2 field. So that means this is just, so I think so I sort of did some unnecessary work here because this 2 is 0. Okay, so this 2 is 0, so I think there is an error here. So here note that. So I think that simplifies this calculation. So you have beta square is equal to a square plus b square. So you don't need to do this, but basically, so there is a mistake here. So this gives me beta square equals a square plus b square alpha square. Okay, but that means u equals a square plus b square t, right? But that is a violation of the fact that u and t are independent variables. So because this relation makes that they are independent, this equation forces them to be dependent variables, but that's not possible because u and t are independent variables. So in fact I didn't need to do all this work. Okay, sorry about that. So there is a small error here. I did more than what is required. I can just use the fact that this must be 0 and directly show that I get a dependence relation between u and t, which is not possible. So I did more work, but I hope that's clear, that is fixed, that you understand the error and you realize that we nevertheless have the result that we want. So go back to that if needed. So now let's come back here. So what we have is alpha plus beta b beta whole square is this, but alpha square is t, beta square is u, so you have t plus b square u, and this of course is in f. So hence degree over f of alpha plus b beta is less than or equal to 2 because alpha plus b beta satisfies a degree, degree 2 polynomial over f. So this concludes the proof that, so we conclude that LB cannot be K because so yeah, this contradicts this. So this we conclude from this argument that LB colon F is not 4 and hence we get a contradiction. So I am sorry, I just sort of messed up at the end here by confusing you with notation, but basically this is the contradiction. The contradiction is that if LA and LB are equal, so what we have essentially proved, LA equals LB implies LB equals K. This implies LB colon K is 4, but this is not the case. But this is not the case, and hence LA cannot be equal to LB. So the set of LA is an infinite set of intermediate fields. Okay, so this, I mean, you can separately prove as an exercise that LA can never be equal to F for any A. You can prove this separately because using the same kind of arguments that we used here in proving that for example K is not equal to F alpha. Okay, similar arguments will give you this, but I claim that this is not relevant. At most you can have one LA equal to F, but because they are all distinct, the other things must be proper intermediate fields. So there is, even though this degree is 4, there are infinitely many intermediate fields. So this is a weird thing that happens for inseparable extensions. Of course, K over F is inseparable. So also check K over F is inseparable, because these polynomials whose splitting field it is normal but not Galois, because it's not separable, it's not Galois. It is normal because it is a splitting field of these polynomials, that you can check, and those polynomials are inseparable. So this is an inseparable extension which is finite yet admits. So think of these LES as sitting in the middle horizontally, right? You can't compare them because there is not enough room here. There is degree 4 extension, but they are all horizontal. They are all in the same level in some sense. Okay, so this shows that you can have a finite extension with infinitely many intermediate fields. So let me stop this class here. In the next class, we will do one more problem which illustrates Galois main theorem, and then we go on to applications of Galois theory. Thank you.